So, in today's lecture we will talk a little bit about VC dimension, and the motivation to this topic stems from the capacity of the machine, in the sense the complexity of the machine, in a way that it can disambiguate the data patterns belonging to two different classes or possibly multiple classes. For simplicity, we consider two different classes and points or feature vectors belonging to these classes, and we are interested in this classification problem. Is there a connection between the number of points in our data set and the type of classifier that we are interested in that can solve this classification problem, right? This is sort of the motivation, right? Is there a link between the number of data points and the complexity of our learning machine? This is the motivation to the problem. So, we will start with a couple of formal definitions that will help us, and then we will begin with some motivating examples to understand the problem at hand. Okay. So, definition: a dichotomy of a set denoted by S is a partition of S into two disjoint subsets. Now, let me consider to illustrate this definition, I consider set S to be x1, x2, so on till x say 100, and I look at a set denoted by S cross as x1, x3 dot 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 till x99, that is I pick up all the odd indices. Maybe we can write this as vector. Okay. Now, and I call S with the circle in the subscript as all those points that I want to pick up with even indices x2, x4, so on till x100. Now, I can have a label, I mean if I want to say that all points in the set S cross are labeled 1 and all the points in the set S circle are labeled 2, that becomes a labeling problem, right. So, x1 gets the label 1, x3 gets label 1, x99 gets label 1, so on, and then x2 gets label 2, x4 gets label 2, x100 gets label 2, and so on, right. This is basically a partition of this set into two disjoint subsets, sort of corresponding to our two class problem, right. This is just a two class problem. So, we will define another term here, and that is the word shattering, and we use this, and we have used this in connection with Cover's theorem earlier, but I think we want to sort of formalize it here. Okay. So, a set of instances S is shattered by a hypothesis space, call it H, if and only if for every dichotomy of this set of instances S, there exists a hypothesis that is consistent with the dichotomy. What it means is there exists H belonging to this space capital H, that means there exists these hypotheses in the hypothesis space capital H, such that for example I use hypothesis H1, this classifies our elements belonging to say this set S cross as maybe positive and hence the label 1, and I have H2 that classifies points in my set S circle as negative, and I assign a label 2 to this, right. And if the hypothesis is consistent with the dichotomy, then I mean we can say that the set of instances in this set S is shattered by this hypothesis, right, by the hypothesis present in the hypothesis space. Now let us see through illustrative examples what is happening. We will look at points on a line and points on a plane, possibly in 2 dimension, and build our intuition towards this idea where we are leading towards classifiers etc., and the connection of VC dimension to this. Okay. Now let me motivate the notion of VC dimension, and by now you already know what VC dimension is. It is Vapnik-Chervonenkis dimension, and I have mentioned this earlier to you that it is a measure of the complexity of the machine, learning machine. Now let us consider points on a line, right. So these points belong to either class S cross or S circle. So I will just mark this here, points belong to S cross or S circle. So let us consider 2 points. For example, I have a cross here, I have a circle. So clearly I have a plane that can separate these 2 points, or a line in this case, right. In whichever orientation, it does not matter, I can separate these 2 points, just 2 points. And it does not matter if I had a circle here and a cross here in a different space, and you know it is still possible, right. So from our definition we can shatter the 2 points on a line. This is no problem. Let us go one step further. I will add one more point to my set. Let us consider 3 points on a line. I think we considered some of these aspects when I discussed Cover's theorem, but I think things become more clear here, you know. So I have a cross and a circle, or perhaps I can have a cross a circle and a cross, maybe I have a cross cross cross, circle circle circle, etc. I mean these are all possibilities. We did this example when we were discussing the boundary conditions, but let us see carefully what is happening here. As again, mind you that we need just one line that can shatter these points, right. There are 8 possibilities, 8 different configurations. Right. We have 8 different configurations over 3 points. Now if I were to have a line that has to separate, this is no problem, this is also no problem. I can just put somewhere here, and all of them on the side of the boundary is all crosses, right. Configurations A and B are not an issue, or other possibilities like you can think of something like this. I have a circle here, and a cross, that is also no problem. Let me call this configuration C, right. Like this you can enumerate, but the point of interest would be configurations like this, a cross, a circle and a cross, or possibly a circle, a cross, a circle, right. Now I am just complementing this configuration here. So now let me put one line here. I have a classification error. There is one point which cannot be classified by just a line. Similarly, consider this case in the bottom, let me say this configurations E and F. So let me say D and D. Okay. So I have problems here, right, because the points are lying on both sides. For example, in this case the cross is lying on both sides of the boundary, and here the circle is lying on both sides of the boundary. So we have a classification error and we cannot perfectly shatter, right, and you can do this example for all the other possibilities and you can conclude, right, and that is the reason why we had this boundary condition 2 times P when we discussed Cover's theorem, right, that those are the points that you can shatter. Now so clearly in this case when I went to 3 points I could not shatter. 2 points was no problem, 3 points there is an issue, right. So these are problem cases. So let me put this in bold here. Problem cases, and this works. Okay. Now let us build upon this intuition, let us play this game over points on a plane, right. Now we have all the possibilities, you know, on a plane, but let us consider some possibilities to get a feel for our intuition here, right. We consider again 2 different classes, points belonging to these crosses and these circles. Okay. So let us consider the following configurations. Let us say this is my configuration A. Clearly I can have a hyperplane which can separate these points is no problem. Okay, but let me start with 3 points. Okay, I'll eliminate this circle here. So I have 3 points, no problem. I will consider another 3 point configuration, maybe a circle here, maybe a cross here and maybe a cross here, like this triangle which is possibly rotated. Still we have no problems, we can have a line which can shatter, and if you just want to change the points, maybe I have 2 circles and then I have a cross, I still have no problem, I can shatter. So 3 points can be shattered in R2. This is no problem. But now, like what we did for the line case, let us increase the number of points and make them 4 points, right. So let us increase by 1 extra point, that is 4 points in R2, right. And let us see the number of configurations we can have. So as I mentioned earlier, we can, this is the simplest case, this is no problem because I can have a line that can separate these points. Possibly if I had something like this, still I have no problem, I can separate the points. But let us consider the XOR configuration that we have dealt with. We have seen this case, this problem in the discussion for designing classifiers when we dealt with MLPs, the support vector machine and the radial basis functions. So 3 times we have considered the XOR problem. So let us see this again. So if I have a configuration like this, clearly I cannot have a line that can separate, this is not possible. Right, it is not possible because with one line I have this cross which appears on both the sides of the boundary and I cannot shatter. So this works, this does not. And similarly let us look at, like I place the points, 3 points like this and I put a circle in between, like the centroid of an equilateral triangle, right. Even this is not possible because if I put a line anywhere, it's you can verify that it is not possible, right. So whichever line that you want to put to separate the points, I cannot shatter these 4 points. Now there is a connection here between the dimension d and the number of points for a linear classifier. So when I am on a line, 2 points was fine, when I went to the 3rd point I had an issue, that was in dimension 1. Similarly when I am on a plane that is in 2nd dimension, 3 points was no problem, 4th point is an issue. And you can convince yourself, you can go to points in 3D and extend this analysis. So I consider 5 points and then look at these configurations, and you can generalize that if I have D features and a bias, then when I have D plus 1, I mean I can for example in a line which is just one dimension here, 2 points was okay, right. When I am on a plane that is dimension 2, 3 points was fine. So when I am in D dimensions, D plus 1 points I can shatter, and anything beyond that I land up with configurations that I cannot shatter. Okay. This is a very important sense of intuition that you can get, but formally you can prove this, and I will leave this as an exercise. So, sort of to conclude here from what we are trying to see, if I consider a hyperplane for shattering points over d dimensions, okay. The equation of my hyperplane is W transpose x equals 0. So, if I expand out, I have summation I equals 1 to d W I x I plus W naught times 1 equals 0, and this is to accommodate bias. And this corresponds to projection of d features onto a vector normal to the plane. Okay. So, what we have from our conclusions is the number of points that can be shattered in RD is d plus 1, and that is an important result. Okay. Now, with this we can define what the BC dimension is. That means there is a link to the complexity of the learning machine, that is in the way in its ability to shatter the points and the number of points in the training set itself, right. So, let me give you a formal definition here. The BC dimension of a hypothesis space H defined over a data set X is the size of the largest subset of X. This is very important, largest subset of X shattered by H. And it is often denoted by BC of H. Now, the BC dimension of a hypothesis space defined over a data set. So, you have a data set and you have a hypothesis space, and you pick a hypothesis from this space and apply it over the data point, and you use this towards classification, right. Now, the BC dimension of this hypothesis space corresponds to the largest subset of your training samples or your data set over which you can shatter the data points using the hypothesis in the hypothesis space. This is a very important definition. So, that means this dimension VC dimension is linked to the number of data points in your training set. Okay, I have not given you a procedure to compute the VC dimension, but there is a result in the theory of machine learning, and one of the important results is the PAC bound, probably approximately correct bound, PAC bound. So, let me write it up here. The reader can refer to the PAC bound derivation. So, this PAC stands for probably approximately correct. In any standard machine learning textbook, right. In any statistical decision theory or statistical learning theory book, you can refer to that book where we discuss this PAC bound derivation, and that links the error in the training set, the VC dimension, and these constants and the cardinality of the hypothesis space, etc. It links all these things together through a bound. Okay. But I think this would be sort of clear to you at this juncture that as you go with to higher dimensions, right. So, there is a link with the number of points that can be shattered by this machine, right. So, now in the context of learning, what sort of machine what sort of learning machines do we have, right. So, for linear classifiers, with points x in a d-dimensional space, the VC dimension over this hypothesis space is d plus 1, where d is the number of features, and for neural networks the VC dimension is sort of linked to the number of parameters in the network, or like it is proportional to the number of neurons in a hidden layer for a single layer perceptron. For a single hidden layer, multi-layer perceptron. So, if you think about in the context of neural networks, I have these nonlinear processing elements in my hidden layer. I also have them in the output layer as well, but the complexity of the machine or the capacity of this learning machine to shatter these points depends upon the number of neurons in the hidden layer. And this example would be very clear when we worked out the 3 XOR problem, right. We worked out the 3 XOR problem and we saw how we can get different decision regions for neurons that can respond to just one input being greater than or equal to 1, at least 2 inputs being greater than or equal to 1, etc. right. So, this is what we considered, and that is a very good exercise to see how we can create this hypothesis within our hypothesis space such that the neurons in the hidden layer can selectively respond to the hypothesis under consideration, right. So, this VC dimension for neural networks depends upon the number of hidden neurons, and you can say it is proportional to the number of parameters in the neural network, right, and that is the complexity of the machine. And we know that if you have one single hidden layer, right, if you have a single hidden layer and you can still approximate any function, you do not need to have multiple layers, right. Multiple layers is only to balance this trade off between complexity and your approximation error, right, and in this case a single layer of hidden neurons is enough. So, in that context the BC dimension for a neural network is proportional to the number of hidden neurons, right, or the parameters in the hidden layer. So, this completes our discussion on BC dimension. So, I think though I have not explicitly given you a derivation as to how the BC dimension can be computed, because this is going to be an advanced a topic in an advanced course on neural networks. So, but at least you would appreciate the fact that given the dimension, the number of points, there is a link between the capacity of the machine that can shatter the points towards the classification problem. Okay.